Okay, so thanks for the invitation and thanks for the introduction. So I will try to give you an overview of what is current status of explainable AI, what are the directions and what we have done in these 3 years of projects. So the context where we are, this research is located is the one of human-centered AI. So we discussed yesterday Virginia Dignum and also Yasmin. So what is the scenario that we are shaping in Europe? And so with this idea of that, the things that the AI system that will be developed and used in Europe should incorporate ethical values as much as possible. So where beneficence, not maleficence, autonomy, justice, and explainability. And in this, this framework has been shaped by different actions by EU, including the legal framework that we have seen yesterday. It started with GDPR, where already there the principle of the right of explanations was born, discussed, but was there. So explicability, it's impact many dimensions of trustworthy AI. It impacts all the area of transparencies and accountability, where so the role of explanation is to make understandable why a model AI system has generated a particular recommendation. It is also impact auditability, because it is also related to the that ensuring that the AI system decision-making process, what is the entire pipeline and the accountability of any points of this path, and it is important for understanding, for the designer, understanding when, if the things are you have done a due diligence development process of AI system. And then also for human oversight, should support the process of trust calibration to support human oversight. So at the end, we don't want a system, AI system, to insert the AI system in a society where at the end the humans interacting with that systems or delegate completely to the system. Okay, so the algorithm say that, and then it's total delegation. On the other side, we don't want, so we want also for successful collaboration, the person which interacts with the system has to trust, not at the end, not so taking its decision, but really having the advantage of using such system. So all this debate started, and also the actions that have brought to the legal framework and also a lot of investment of in Europe in the national strategies, all with this idea of trustworthy and human-centered AI, as due to the fact that so can we trust AI? So we know that the data-driven AI, so the machine learning models, they learn from data correlations, and they learn what is on the data. They can be affected by the bias which are in the data. So there are several examples now which are a sort of a manifesto of why we shouldn't trust completely, and we should put in place any form of other requirements for avoiding such problems. So the example of learning, the image recognition, distinguishing ASCII dogs from words which fails, and then it fails because it fails in a situation where the background of an ASCII dog was the snow, exactly as the many pictures that were exposed during the training phase to the system, so that the system indeed didn't fail. The system was very, very efficient in finding the characteristics of images which were particularly efficient for predicting wolves. There's no in the background. So we don't want to have this kind of failures. And the other examples, the compass case, where the compass was a system for helping judges for predicting the risk of reiteration of crimes. And then there was the journalists from ProPublica, they auditing the system several times, they demonstrated there was a bias with respect to the race. So the white people had a lower high risk systematically, same profile, systematically they had the lower high risk of reiteration than the black people. So again, this was a big debate, but the system learned by the data it was trained. So the problem is that so there is the risk of data bias, which is amplified, but dramatically amplified by the machine learning, which tries to be very, very efficient. So the problem is how to avoid this. So we need to have a way to inspect the models in order to create a robust system, to not have this kind of failure. So the problem is that many systems are black box, but dramatically black box. We discussed this morning the large language models, but even many other deep neural networks are enormous. So learning from data means being exposed to plenty of examples that some human or someone else has annotated, and so we know certainly the outcome. We say this as being labeled by someone. The black box, the machine learning learn the functions which is hidden in such data, which is a complex function because those data are pictures, maybe very complex form of data, and then the learned function, the black box, is capable, given a new instance which is not for which the instance is not known, to provide such. So this is the game of the learning from data, and this learning may be extremely complex, like a deep neural network. The model, the black box there, it's millions of nodes with parameters which cannot be really understood. Or maybe there might be also another form of black box. Some of those methods, of those boxes which have been learned, they are proprietary. So really, we do not have the access to the training data, to the internal of the box. So there are those two kind of black boxes which are on the table, and if we want to avoid that, to be capable of or respecting or transforming the outcome in something which is human understandable, we need to find a way to capture such information. So this area of explainable AI, which started in 2015, 16 with this name, explainability, has already been an issue of many artificial intelligence methods. So it's not new, but it started to become a sort of area by itself, with this idea of being capable of inspecting and being capable of explaining in a human understandable terms, so the reasoning which is behind the black box. So, and this is the big area. But now start to the end. What is an explanation? So we need methods which are capable, out of this box, which are black box, so complex, we need to provide, first of all, an explanation to see what it is. The problem is that even what is an explanation is not a clear answer, because an explanation strongly depends by who is asking for. So it may be a story, maybe an example, maybe some mathematical representation, and all those different forms of explanation are reasonable. They strongly depend by a good explanation for whom. So it depends by who, by its background and the goals. Maybe the data scientists, the developers that needs to inspect this complexity which is behind, or the end users that at the end the explanation it's part of the further actions, and such actions so need to be supported, even legally there is also legal responsibility. So I mean, I'm being treated fairly. What can I change for obtaining a different outcome? Or the auditor, which won't verify that the entire process has been developed with due diligence and all. So all those three type of users may request an explanation. So, and there are, now I will show you plenty of different proposals which are there in literature so far. So there is an area of which proposes explanation in terms of the feature space, in terms that. So I'll try to show you with respect to your attributes. So you give me an instance, you want to predict. You ask me to predict the risk of loan. I decline your loan. So I'll try to explain why I will decline the loan, trying to explain with respect the characteristics that you have. So your age, your weight, I don't know, any kind. So the feature that describe the object on which we are asking to the system a prediction, a recommendation, a description. So, and this it comes, so there are several methods that give you the sort of weight, a positive weight, which contributed to that outcome, and also negative weights, which contributed to having, so, and give you a sort of way to decrease or decrease such weight of these characteristics, relevance of these. So separating attribute by attribute, what has been the contribution to that? This is an example which is very useful on this, is on data, on image data. The way this feature relevance is provided, it's using, so it's providing this explanation. They are called saliency maps. Essentially, you see, so now, for example, look to the Junco bird. So there is a system which has been trained to recognize images of birds, of animals. So now you ask, you give this to the system this image, and then you will obtain as an answer. Those are all examples of explainers, of explanations produced by different algorithms. They try to highlight which portion of the images was responsible for giving you, for deciding, by the system deciding that was a Junco bird instead of something else. And so there are different proposals. The research there, it's a competition on being more accurate on these saliency maps. In the case of text, the explanation is a form of, I try to highlight you the words of the test. So I'm predicting that this test has a positive sentiment. Suppose we are a sentiment, a classifier for sentiment or opinions. So this test, or in this case, it's a movie. I recommend you to see this movie. Why you recommended me to see this movie? And the motivation are highlighting the text, in the text of the abstract of the movie. So, or in other cases, it's an explanation as a prototype. So we change now, not anymore a relevance of features, but now I give you examples. I can give you examples as a. So this is a Junco bird because this part of the pictures in my training set, all the images which this similar with the neck similar to this one were labeled as a Junco bird. Or so, and then you can also show the saliency maps, what was particularly relevant. Or an explanation can be something more multimodal, something which combines text and images, so start to get richer. So it's a story which combines the two things. Of course, it is richer because it has knowledge that can be used for reaching such an explanation. So it's an image plus so it's, for example, there is a knowledge graph behind which allow you to construct such rich explanation. Or explanation can be in the form of counterfactual explanation. This is another important way to produce explanations, because it activates a different way to reason. So it's sort of what-if analysis. What was positive and what was negative, and what can you change for obtaining a different outcome. So your long has been rejected because those features were too high. Those features could be changed, could be increased, other features could be decreased. So, or again, in the form of a counterfactual, you can give rules. So that express the factual and counterfactual explanation. So you have been declined because your age, because so you can change your age within a certain range. You can do so, activating this form of reasoning. Other than counterfactual can be also counterexamplars. So, for example, I can give this image. So not anymore the Junco bird, but it's an image, a skiing spot, which was predicted. It has been predicted to be this form of cancers with very high accuracy, 99%. Why? Why? And then it shows you exemplars which were similar to with that outcome, and counterexamplars that were images with a different outcome. It is very difficult to find counterfactual, because counterfactual has to be something which is usable. So if I find a counterfactual that is too far away, it's not useful for your cognitive process. It has to be something which is it has the minimal change, something which is feasible, some feasible change that you can do for obtaining a different outcome. Cannot be very distant. So there is a lot of research in this area to find more so appropriate counterfactual, actionable. We call them actionable counterfactual. So this is something that some of the examples that we pursue in this project. But in the project, we have also another ambition. So with this idea that, so we call them the Dr. House model, that the explanation is just a starting point for establishing a collaboration with humans. So the Dr. House is a very intelligent agent which interacts with other intelligent agents which provide explanation, provide hypotheses, provide also some counter examples. So with this idea of, but at the end, the responsibility is on the shoulder of Dr. House. So there is this. So the idea is that having a conversation where the machine and the human have the human is exposed to different form of explanation, the one that we have seen before, but also can start to interact and ask. So can ask questions and interact. So this is the case of compass. You may recognize. So the classifier say, okay, this one it's a high risk of recidivism. Why? Because of the age. So there is a rule which describe the features, the characteristics of that person. So she was younger than she's younger than 38 and younger than 38. The blue color. She's already a recidivist. Okay, so the user start to ask new questions. So, but now show me exemplars. Show me a training exemplar. So you have you show similar instances and dissimilar instances. So you start to be even more suspicious that there might be something wrong in this proposal that the system does you. Then you start to ask, okay, what about if I remove this feature or not? So this maybe even implies a retraining or redoing something, and then the system, okay, even if what happens if you don't consider, for example, the age, and then you see that just the color was determinant for the system. So this is just a very simple example. So what we are doing there, essentially working both on the algorithm, but also on this other, which languages should we use for creating this collaboration. languages that has to have a very high expressive language, which are also capable of highlighting the causality which may be in the decision. Okay, and then of course we are also creating some other platform for creating different experiments. And we have a special line where we do use cases, but use cases are not meant just for experimenting the methods, for involving on particular applications, involving users, end users, and trying to measure this idea of trust, with having in mind that as we are designing not only an AI system, a person AI system as a unique entities. So we have to measure, to validate the two things. We have also to find the method for doing this validation, which kind of trials, which kind of methodology for observing them. So what time, how much do we have? Okay. Okay, now I will give you an idea of what are the methods there which are capable of producing the form of explanation that I said. So there are two big families in literature currently very productive. So there is one area which is trying to do what we call explainable by design methods. Essentially, so you have your very complex deep neural network. You try to transform step by step such deep neural network in such a way that at the end you have a model which is interpretable. Having a model interpretable means that once I have the answer, the prediction, I also have the explanation, because it can be naturally extracted by the model. That means it's not 50,000 parameters and weights. It has to be something very more simple. Or simpler. And the other big family of methods is the one that, okay, I like the deep learning methods. I like the black box, which are very efficient, and I find a method to I define a new software, a new system, an explainer, which add an explanation to the black box, keeping the black box as it is. I'm not going to redesign. I keep as it is, but define the sort of twins, a digital twins of the digital predictor that is capable of providing explanation. I'll try to. So, and there are various details. Of course, all those methods are strongly depending by the form of data they are working. So there is a huge arena of methods there, because for each of data types there are different families of explainers that can be used. So here in this benchmarking survey, we also try to see by form of explanation, also to provide metrics for measuring the quality of explanation, which is another critical point. Okay, so you can have for graph, test, time series, images, tabular. So I'll give you just the intuition how the post-hoc explainer works, because essentially they do exactly as the Compass guys made with the journalists made with the Compass. So you set up, you start to auditing, to ask to the deep, the black box, ask a lot of questions till you have enough positive or negative answers. And now from this set of positive and negative answers, you reconstruct your predictor. It works if the predictor that you construct is one of these is explainable by design, is an interpretable one. So you are capable of constructing a very simple method, which is easy to be transformed in one of the previous explanations. So the criticality here is that, so the intuition here is that you are not doing this for the entire space of your training set, but you do locally. That means that you don't want to, so here in this image, the blue and the pink represent what is the decision board, which is in your data. And the board, so the board is the one that the black box has approximated. We decide, so we do it locally. So you do this auditing, given the fact that you have received a question by the user. The user asks you to predict something, and then you just try to explain this prediction doing this process, generating a lot of points locally to this instance to be explained, and then there you construct the answer, the explanation, which may be in the form of factor or counterfactor, and then there are and then out of this, then this method, these local explainers, which does these interactions. You can construct also global explainers, constructing plenty of local explainers and combining them. And then there are there is an interesting line which does the same idea using latent space. This is a little bit more complicated because sometimes the number of attributes, the number of features may be so huge that generating these points and generating the simpler example may be too complicated. So you move everything on a different space. We call it latent space, which is with less dimensions. We generate explanations there, and then we are capable of generating exemplars and counterexemplars, as you have seen before. In the area of transparent models, they are trying to use a knowledge graph, and in order to connect, to glue some portion of the actions of the graph neural network to knowledge which is on the logic graph. There is a knowledge matching between what has been learned by the neural network and what is in the graph. So there are various experiences. Essentially, the idea is being capable at any layer of the learning of the neural network, being capable of attaching some semantics using the knowledge graph. It's an very interesting area, but it works for specific domains. When you are in specific domains, so you have enough knowledge graph, it works. It's not a general approach as before. Okay, so now I want to give you an example of an explainer and how to involve the users, because I think this is can capture what it can give you the idea of what is going on in this area. So the explainer, so the black box is something. It's a black box. It's a Dr. I. It's a neural network. It's a convolutional neural network, which was trained for and was actually was a product. Is a product for working on sequential on the sequences of data records of a patient. We are in the medical case, so you have a lot of visits, and at each visit there are several data which are collected, and each patient is an history. So observing the history of this patient, trained on the history of many patients, it is capable of this recurrent neural network of predicting what will be your next problem. It's a next step. Which kind of your risk of having some form of illness. It is also a multi-label in the sense that there are comorbidity, they call in health, so you don't have only one. The symptoms may have different forms of illness. So, and this is capable of explaining this. It's quite good, a famous system. So now we add the explainer to Dr. XI. So we keep it as it is. We do the game of asking a lot of times, and then we create a system that from the sequence of the data, it's capable of adding the so the Dr. XI provide a prediction. So next time there will be diabetes will grow like to this status, and then you'll have a non-alcoholic liver disease. That's the prediction. And the explainer provide you, observing the history of the data, of this individual data, will provide you the explanations that in terms, okay, so of these characteristics of the physician. The nice thing is that this is done using the language of the physician. We use the ontology, the same ontology that the physicians are using, and also the explanation is provided using that ontology. So, and then there's also some visual interface that highlight you what are the responsibility of the various but what I want to show you is the fact that now, once we have done the system, so we made also the use case, the trial involving some expert users. They were nursery physicians, very well trained on the health case. So with this idea of the question was that is the explanation impacting user trust? So again, as I was saying begin, if you have too little distrust, so that means you have a sort of algorithmic adverse. You will decide by yourself, no help by the system. And if you have too much over resilience, it doesn't have any advantage. So the physicians is not really learning nothing with this explanation. It's simply demanding to the system. So the experimental design is that we had 20 healthcare professionals, and then how it works, the methods. So we give them the history of the patients, and then we ask the first round was asking them their evaluation, which kind of they initial estimate for next step. So they gave Then we divided in two blindly. So some of them we gave the recommendation of the AI system with the explanation, another part without the explanations. And then we have the final outcome. Now, so the question is that has been influenced or not the professional by the explanation that we provided. And then there is a way to measure the trust, which is in psychology, it's used in psychology, which is try to measure the degree of advice. Essentially, you try to observe how much the opinion has been changed before and after the trust, and then in the two situations. And then with the explanation, they changed more. So the explanation was really influencing more than the simple prediction. The experiment was designed by a psychologist, not by the computer scientists. Actually, the computer scientists, we were thinking to add a lot of very fancy interface, making them richer. So, and then he removed all the fancy part of our interface. It was a really ugly interface, very simple, so simple, with this idea not being influenced by other factors. So this should be very, very simple. So simple that at the end, one of the questions they said, but a little bit of a nicer interface was one of the further recommendation. But however, I think it was right in terms of measuring what the trust was perfect. So now what next? What next? So so essentially in this 7-8 years of contributions of this wide field of XI has brought to the idea of having a sort of new machine learning process, which also include, once you have done so your machine learning has also to include explainable models that may be in the form of things that I have showed before. So models which are capable of producing, let me say, raw explanations. So capturing the signals inside the black box to produce explanation. Given an instance, we have some form of explanation to provide. But it's not yet the end of the story. Now we have to think to the interface. So now we want to have a collaboration. So the explanation has to be visually very well rendered, and also and also we have to think to the interaction, as I was saying before. So this form of a conversation. So next challenge, the challenge are now being capable of modeling, so the entire process of decision making, and thinking to our classifiers enriched with explainers, with different forms of explainers that are capable of communicating the level of uncertainty which is behind the decision, communicating when defer a decision, so that are capable of asking to the humans a second opinion, and are capable of accepting this second opinion. So keeping the human in full control, so having a clear picture to show when the system succeeds, when it may fail, when to trust and when not to trust. Okay, so this is on the machine learning side. So current machine learning, so there is an area which is called hybrid decision making, which is aimed to design machine learning methods capable of doing this. So the second challenge is to design the interface toward the users, putting in the game also the psychology theories for decision making. So there are plenty of research there that may be used. So it's are we fostering one process of decision making towards a different one. So we have to be aware in the design of the system what is the kind of interactions, and possibly co-designing that with the users. So that brings to a problem that this area is not anymore computer science or machine learning area. It's not enough to be capable of capturing explanation by the machine learning methods, but we need also to insert other disciplines collaborating with us. Human-computer interaction, it's one, but also psychology and cognitive science. So it becomes a more interdisciplinary research. So the third challenge is that the validation of the system. The Turing test that is still adequate for this human-centered AI. Turing test was aimed, so I know what is intelligence, that the system is intelligent, if given two different outcome by two systems, I am not capable of distinguishing if it's produced by human or not. Do the example with ChatGPT, and that will be very difficult. But this is not enough. Now we want to see if the system plus the humans obtain a better decision. So we have to change what to measure. It's not to measure; it's measure the outcome of the combination of the two systems. And there's we have another issues, and then I will conclude saying that. So we have to be aware, exactly trying to repeat what we said yesterday in the panel. So so designing having this human-centered AI means to have the attention to the fact that humans and society may be impacted by what we are designing. So we don't have to find techno solutionist, but try to provide gentle work towards gentle technology to find us to help humans. This is the work of many people, and so I'm going to conclude, and here you can find the name and also the biblio that has been done. So, thank you.